Alright, so in this video I'm going to be explaining another important article with the title Learning Graph Representations for Influence Maximization. This ICLR paper in 2022. As the field of machine learning for combinatorial optimization advances, traditional problems are resurfaced and readdressed through this new perspective. The overwhelming majority of the literature focuses on small graph problems, while several real-world problems are devoted to large graphs. Here we focus on two such problems: influence estimation, which is an NP-hard counting problem, and influence maximization, and an NP-hard problem. We developed GLIE, a graph neural network that inherently parameterizes an upper bound of influence estimation and train it on small simulated graphs. So what is this cost-effective lazy forward algorithm? It's used to select some seed nodes in a network as propagation source to reach as many nodes as possible. This is known as influence maximization, where influence represents anything that can be spread across the network, such as contamination, information, disease, or anything. CELF was proposed by Yuri Leskovic. He is one of the greatest minds in the world in the field of graph neural network and graph representation learning. It improves the traditional greedy algorithm based on the ICE model by taking advantage of the submodularity. It only calculates the spread score for all nodes only at the initial stage and does not recalculate for all nodes afterwards, hence cost effective. So we address this IM, influence maximization, using neural networks to capitalize on aforementioned advantages as well as their ability to easily incorporate contextual information such as user profile and topics, a task that remains unsolvable for non-specialized IM algorithms and heuristics. So we introduced this GLIE. A is just adjacency matrix, X is the features of the nodes, representing which nodes belong to the seed set by 1 and 0 otherwise. So the way we are creating our features is this special type. So we can use message passing to compute a well-known upper bound, which is p hat of pu condition on S. Because as S is our seed set, so they have a corollary that says the repeated product computes an upper bound to the real influence probabilities of each infected node at a step t plus 1. We can thus contend that the estimation provides upper bound on the real influence probability, and we can use it to compute an upper bound to the real influence spread of a given seed set, for example, the total number of nodes influenced by the diffusion. Since the message passing can compute inherently an approximation of influence estimation. In our neural network architecture, each layer consists of a GNN with a batch norm and dropout omitted here. So the readout function that summarizes the graph representation based on all nodes representation is a summation over all the final representation with skip connection. And this representation captures the probability of all nodes being active throughout each layer. The output that represents the predicted influence spread is derived by this ReLU of HW. So this is very important. The output that represents the predicted influence spread. So the original cost-effective lazy forward, the 2007 algorithm, is an acceleration to the original greedy algorithm that is based on the constraint that the seed spread will never get bigger in subsequent steps. The influence spread is computed for every node in the first iteration and kept in a sorted list. In each step, the marginal gain is computed for the node with the best influence spread in the previous round. If it is better than the previously second node, it is chosen as the next seed because it is necessarily bigger than the rest. This property stems from submodularity, that the marginal gain can never increase with the size of the seed set. If the first node's current gain is smaller than the second previous gain, the list is resorted and the process will be repeated until the best node is found. The worst case complexity is similar to the greedy, but in practice it can be hundreds of times faster while retaining greedy's original guarantee. So we propose a straightforward adaptation where we substitute the original CLE of IE based on MCIC with the output of GLIE. We redirect the reader to the Appendix B, where we show that the estimation of GLIE are monotonous and submodular in practice, and hence sigma hat is suitable for optimizing with CLEF. Since we do not prove the submodularity of sigma hat, we cannot contend that the theoretical guarantee is retained. But it has two main bottlenecks. First, although it alleviates the need to test every node in every step, in practice it still requires IE for more than one node in each step. Second, it requires computing the initial IE for every node in the first step. We will try to alleviate both with the two subsequent methods. So this is a visual depiction of the pipeline. The layers of GLIE are depicted by a heat map of an actual seed during inference time, showing how the values vary through different nodes. And then your action is the new seed. We will go through this QNet and then seed influence, candidate seeds. Here we do influence estimation, but compute for every candidate seed before this Q network. So it's interesting because you're using graph reinforcement learning for influence maximization. So we develop a method that computes only one influence IE in every step, along with the initial IE for all nodes. We first utilize the activations mentioned above to define the influence set representations, which can be computed by adding the activation of each layer, summing along the axis of the hidden layer size, and thresholding to get a binary vector. Once you have these activations, you can get just using this thresholding technique to get some binary vector, because at the end of the day what is important is those seeds, and you can obtain it by the binary. If it is 1, then it is selected, where T is the number of layers. So this vector contains a label for each node whose sign indicates if it is predicted to be influenced. We compute the average representation because d sub t varies through layers, and since we add all layers outputs, we need an equal contribution from each layer's dimension to the final output. We utilize this to compute the difference between the influence of the current seed set and the initial influence of each other node. So the Q network first I should say that the Q network produces Q value. Reinforcement learning, you have either value-based method, or either policy-based method. And there is something in between that shares both of them, which is called actor critic. Actor refers to the policy, critic refers to the value. And yes, this is also similar to what your brain does, because I've written an article in Medium to explain how actor critic is implemented in your brain. And here they only care about this value method. I mean, things like Q value methods and Q network. And so here we are creating the Q network, which is called graph reinforcement for influence maximization. And so we have this Q value. Because you have a set S, you have a graph G. And then you can calculate Q. So we utilize a greedy policy to choose the next seed. So this is our policy, by the way. Condition on your seed set, you have your action. And then given the chosen action U, the reward is computed based on the marginal gain. The estimated influence of the new seed set minus the influence seed set before the action, like this. So this is the reward. During training, we use epsilon greedy to simulate an IM game and balance between exploration and exploitation. We store as a train tuple the current state action embedding, the new state embedding, along with all next possible actions. So the strategy to pre-train a graph encoding layer on a supervised task and use it as a part of the Q network has proven to be beneficial in this article, Mir Hosseini in 2021. So what is this PUN, which is potentially uninfluenced neighbors? Computing the influence spread of every node in the first step is too computationally demanding. We thus seek a method that can surpass this hinder and provide adequate performance. We first need to redefine a simpler influence set representation. Let L be the binary vectors with ones in nodes predicted to be uninfluenced and nodes predicted to be influenced, respectively. So now we can use this L hat and message passing to predict the amount of nodes neighborhood that remains uninfluenced. For example, that PUN, potentially uninfluenced neighbors, weighted by the respective probability of influence for a node U. And then they proved that the influence spread is submodular and monotone. So for small graphs, they use this dataset, Crime, also GR Colab. For large dataset, they use YouTube, Facebook, and email. And this is the average mean absolute error divided by average influence and time. And this is the influence maximization for 20 seeds with CELEF.